In lesson 3, we're going to talk about how we classify reactions. There are a bunch of reactions out there, so classifying reactions help us understand what's going on in reactions, and it also helps us to be able to predict the products of different types of reactions. There are 5 basic types of reactions that we're going to talk about in this introductory course. They are the synthesis reaction, the decomposition reaction, single replacement, sometimes called single displacement, double replacement, sometimes called double displacement, and lastly, combustion. I like to use relationship analogies to help you understand the first 4 of those reactions. The first one is the synthesis. I call this the get-together. I have this picture of a guy, he's got the hots for the girl, and in the end they wind up dating, so they are together. Technically, a synthesis reaction is when 2 or more reactants combine to make one product. My example there is calcium plus oxygen getting together to make calcium oxide. Now before we go any further, a couple things I want to make sure you understand. In this particular example, when I talk about pure calcium and I talk about pure oxygen, those are both elements. They are getting together to make a compound, something that has 2 or more different types of atoms that are bonded together. Even though when I write that balanced chemical reaction, we wind up with 2 calcium oxides in the bottom, we ignore the coefficients when we're trying to classify reactions. So when I'm saying that it only makes one product, what I'm looking for is the fact that there are no pluses over on the right side. There's only one type of chemical substance in the product side. Second type of reaction is the opposite of what we just talked about. In this second reaction, we have this lovely couple and they have decided to part. This can happen in a couple of different ways. Whenever I'm representing these relationships with boys and girls, I'm representing ionic compounds. So in the top picture, that would be an ionic compound that breaks apart into its metal and its nonmetal component. In the bottom picture there, I would be representing, for example, a covalent substance. We have the 2 BFFs there. They get into a big argument and decide to go their separate ways. Technically, a decomposition reaction is when one reactant breaks apart to make 2 or more products. The example I've shown you here is the electrolysis of water. Electrolysis is just zapping water with some electricity, and electricity is nothing more than the flow of electrons. That's why we represent it with that little E with a negative sign over top of my yield arrow. In this example, I have one reactant, water, and it's going to break apart to make hydrogen and oxygen. Even though I have a 2 in front of my water as a coefficient, recognize that I only have one type of reactant. So another way to think about this is one type of substance is breaking apart to make 2 or more different products. The third type of reaction is a single replacement reaction. I call this the cut-in. My students sometimes like to call it the cheater. In the top picture there, I have this fun-loving guy. He's kind of got the hots for the smart girl. So in the end, what winds up happening, my 2 guys are switching places. The fun-loving guy winds up with the smart girl, and the guy with the hat just is hanging out by himself. The other way a single replacement reaction can happen is when the girls switch places in my relationship analogy. In the second example here, Betty and Wilma are going to switch places so that in the end, Fred is with Wilma. Technically, a single replacement reaction is when an element and a compound get together to make a new element and a new compound. When I look at this first example, I have sodium, which is an element. That would just be pure sodium. I mix that with magnesium hydroxide, which is my compound. And I wind up with magnesium, which is an element, and sodium hydroxide, another compound. Likewise, I can look at example number 2. Fluorine is only one type of atom, so that is an element. Sodium chloride is a compound. I make it a new compound, in this case sodium fluoride, and a new element, which is chlorine. To classify reactions, you really do have to remember the difference between an element and a compound. Elements are when you only have one type of atom present. Compounds are when you have two or more different types of atoms present. The other thing I'm going to point out to you here is notice that in the first example, sodium, which is a metal, is trading places with the other metal. In the second example, fluorine, which is a nonmetal, is trading places with the other nonmetal in the compound. Double replacement reaction is what I like to call the double date gone bad. In this case, when I look at the first example, I have the guy with the funky girl, and then I have the crazy dude with the nice sweet girl. Well, in the end, what happens in this case is the two kind of funny and crazy looking swirly people here get together, and then my very nice, sweet, handsome, gentlemanly looking guy gets together with the sweet girl. In the second example, I'm showing you the same thing. In this case, basically my inside guys, the ones that look like they're kind of studious with their book bags, are going to get together. And then my skater dude is going to get together with attitude chick. Notice in this case, we're dealing with the boy-girl combination, so this typically happens with all ionic substances, metals and nonmetals, and you can think about it as the metals trading places or the nonmetals trading places, whatever works for you. What winds up happening in each case is the pluses and the minuses switch partners. In a double replacement reaction, we start with two different compounds. Compounds are just two or more different atoms that are chemically bonded together, and we wind up with two new compounds. The examples that I have there, I have calcium chloride and silver nitrate, and what's going to happen is they're just going to switch partners. Remember that calcium's the positive ion, chloride's the negative ion. In the second compound, silver's the positive ion and nitrate is the negative ion. So when they switch partners, silver gets together with chloride and calcium gets together with nitrate. In the second example, I'm just showing to you in a formula equation. Again, calcium's the metal or the positive ion, hydroxide is the negative ion, cobalt's the positive ion, nitrate's the negative ion, so they're just going to kind of switch partners here. Calcium gets together with nitrate and cobalt gets together with hydroxide. The last type of reaction is a combustion reaction. Technically, a combustion reaction is when a substance combines with oxygen and gives off a large amount of energy in the form of light and heat. For this class, we're going to simplify it a little bit, and we're going to limit our combustion reactions to just hydrocarbons reacting with oxygen. Hydrocarbons are nothing more than covalent substances that contain hydrogen and carbon. Whenever we have combustion reactions, we have a hydrocarbon plus oxygen gas, giving us carbon dioxide gas plus water. Again, I can have any number of C's and H's, and that's what those X's and Y's represent, reacting with oxygen to produce carbon dioxide and water. The example I have there is CH4, otherwise known as carbon tetrahydride, or methane, the stuff that comes out of our gas jets here in the lab, reacting that with oxygen, giving us carbon dioxide and water. Produces lots of energy and heat. We see that as the flame when we light our burners. The nice thing about combustion reactions is that whenever it says combustion of, you have to automatically know to add the oxygen, it makes carbon dioxide and water. Balancing is what's really nice here because I can actually tell you a surefire way to make sure you always get a balanced combustion reaction. We're always going to start by balancing carbon, then we're going to do the hydrogen, and then we're going to do the oxygen. Now sometimes you run into a little hiccup here, and in that little hiccup what happens is that you need an odd number of oxygens in your reactant. Well, whenever that happens, just multiply your hydrocarbon by 2 and start over, and it should balance every single time. The first example I have here is the combustion of tricarbon octahydride. When you take your exam for this unit, this is exactly how I am going to give you the problem statement. Again, you have to know tricarbon means 3 carbons, octahydride would be 8 hydrogens. I'm reacting that with oxygen gas. I'm making carbon dioxide gas and water. You have to actually complete that reaction. I only give you one reactant in this case. Again, even though I'm starting with one reactant, the word combustion of means add oxygen, make carbon dioxide and water. Well, I'm ready to balance this reaction, and I said we're always going to start with balancing the carbons first. When I look on my reactant side, I have 3 carbons, but on my product side, I only have 1. So let's try and balance carbon first. I can do that by adding a coefficient of 3 in front of the carbon dioxide. The second thing we're going to balance in a combustion reaction is the hydrogens. On my reactant side, I have 8 hydrogens, so I need to get 8 hydrogens on my product side. Well, I know that 4 times 2 will give me 8 hydrogens. Last thing I balance in a combustion reaction is the oxygens. Remember that I have oxygens in both terms of my product here, so I have to take that into account. In the first term, I have 3 times 2, which is 6 oxygens, and in the second term, I have 4 times 1, which is 4 oxygens, a total of 10 oxygens. So I need to get 10 oxygens on my reactant side. Hopefully, you remember that 5 times 2 will give me those 10 oxygens. Last thing I'm going to do here is just double check myself, make sure I didn't make any mistakes. On the reactant side, I have 3 carbons, 8 hydrogens, and 5 times 2 is 10 oxygens. On the product side, I have 3 carbons, 4 times 2 is 8 hydrogens, and again, I'm just going to double check my math. 3 times 2 is 6, 4 times 1 is 4, for a total of 10 oxygens. It all looks good and balanced. Second example is combustion of liquid C8H18. Again, whenever I see the word combustion, I have to know to add oxygen and to produce carbon dioxide and water. Ready to balance this reaction? I'm going to start by trying to balance carbons first. There are 8 carbons on my reactant side, so I need 8 carbons on the product side. Then I do hydrogen. There are 18 hydrogens on my reactant side, so I need to figure out what number times 2 gives me 18, and that would be 9. Lastly, I'm going to check out my oxygens. 8 times 2 is 16, 9 times 1 is 9, and I wind up with an odd number of oxygens. Well, whenever we balance reactions, it's the simplest whole number that will give us the correct number. If I put a 25 here, that gives me 50, so that can't be right. So this is a case where I'm just going to kind of rewrite this equation and start over. I'm going to put a 2 in front of my hydrocarbon and then balance it again. Now, on your papers, you don't necessarily have to rewrite this equation. However, students who get a little bit lazy and don't take the time to do this usually make kind of silly mistakes. So I'm ready to start over. On my reactant side, I have 2 times 8, which is 16 carbons. So I'm going to put 16 carbons on my product side. Hydrogen is next. I have 2 times 18, which is 36. So I need to put an 18 in front of water so that I can get 36 hydrogens on my product side. I'm ready to check out my oxygens. 16 times 2 is 32, and 18 times 1 is 18. That gives me a total of 50 oxygens. Well, to get 50 oxygens on my reactant side, I would use a coefficient of 25. Last thing I'm going to do here is just to kind of double check, make sure everything's all good. On my reactant side, I have 16 carbons. 2 times 18 is 36 hydrogens, and 25 times 2 will give me 50 oxygens. On my product side, I have 16 carbons. 18 times 2 gives me 36 hydrogens. And I'm just going to double check my math. 16 times 2 would be 32. And 18, when I add those up, I get 50 oxygens on my product side. So that one's all balanced and we're good to go. That's all I have for you tonight. Come in tomorrow, we'll do some more practice on classifying reaction and balancing combustion reactions.